these set of notes are going to go over covalent bonds and briefly metallic bonds at the end of these notes as well. So covalent bonds happen between a nonmetal and another nonmetal. So these are not going to be ions that are forming. So ions are only for ionic bonds. In this case, it's going to be a nonmetal to a nonmetal. So again, you're looking to the right of that staircase. And that's going to be the easiest way to identify whether or not you're looking at ionic bond, which is going to be a metal to a nonmetal, versus a covalent bond, which is going to be a nonmetal to a nonmetal. And these are going to be atoms only. So again, no ions. The bond happens because there ends up being an attraction between the nuclei of the two atoms and a shared pair or multiple shared pairs, but between shared pairs of valence electrons. So again, it's the attraction between the nuclei of the two atoms and the shared pair of valence electrons. And again, it can be multiple pairs. I'll put the S in parentheses. So I'll talk about the picture in a second, but how can atoms share electrons? What ends up happening is when we talked about orbitals before, the electrons end up being in overlapping orbitals. So that's going to take us to our picture over here to the right. So this nucleus here is attracted to valence electrons, and we're going to say that because they're nonmetals, they both have very high electronegativities, right? So everybody to the right of the staircase, their electronegativity values are really high. So nonmetals have high electronegativities, other nonmetals have high electronegativities, and what that means is that we're really attracted to our valence electrons. So you can imagine that this atom right here is really attracted to these valence electrons, to its own valence electrons and to other elements of valence electrons. And this element is the same. It is attracted to its valence electrons as well as to other atoms' valence electrons. So what ends up happening is that these orbitals are forced to overlap. So these electrons exist also in this orbital as well as this orbital, and they're forced to sort of stay in this region of space that is forcing these two atoms to be near one another. So if one atom is unwilling to let go of the electrons and the other atom is also unwilling to let go of the electrons, then they're forced to be near each other, and that is how the bond forms. So this is our bond forming when those regions of space are forced to overlap because they are sharing valence electrons. All right, so when we have a covalent bond, we've got the formation of a covalent compound. This is also known as a molecular compound. So those terms are often interchangeable. Examples of other covalent compounds are things like H2O or CO2, or I'm just going to throw this sugar in here. These are all examples of covalent compounds. They're all nonmetals bonded to other nonmetals. Now, covalent compounds get a little bit trickier because there are actually two types of covalent bonds that can form. You can have nonpolar covalent bonds, and you can have polar covalent bonds. So I'm going to start with nonpolar covalent bonds because I have that one written first. This is when when the electrons that are being shared, the shared electrons are being shared equally between the two atoms or between their two nuclei, because the difference in their electronegativity is less than 0.5. So the difference in their electronegativity values is going to be less than or equal to 0.5. So I'll give you an example of that. If you have a hydrogen bonded to another hydrogen, both of their electronegativity values are the same. So if you go back to hydrogen up here, you can see that its electronegativity is 2.1. So if this atom's electronegativity value is 2.1, and this atom's electronegativity value is 2.1, Then 2.1 minus 2.1 gives me 0. So their difference in electronegativity is equal to 0. 0 is less than 0.5. That means that they are sharing those electrons equally between the two of them. I'll do one more example. So we've got carbon and sulfur. So again, I'm going to look at my electronegativity chart. I can see up here that carbon is 2.5 and sulfur is also 2.5. So when I come down here, I can see that their difference, 2.5 minus 2.5 is 0. So again, their difference in electronegativity is less than 0.5. So that means that they are sharing the electrons equally, which means that this is a non-polar bond. All right, polar bonds are clearly one we're not going to share equally. So polar bonds are covalent bonds. Sometimes you'll also hear them referred to as a dipole. And I'll show you what that looks like in a little while, but dipole is referring to the idea that there are two poles. And for us, those two poles, one's going to be a partial positive, so that's a weird delta symbol. Partial positive, I think it's a lowercase delta, and then a partial negative. So those are going to be my two poles. One end is going to be a partial positive, and one end will have a partial negative. So in this case, the shared electrons are being shared unequally between the two atoms or between their nuclei, and that's because their electronegativities have a greater difference. And so in this case, if their difference in electronegativity is greater than 0.5, then they're going to form polar covalent bonds. So the more electronegative atom, what ends up happening is that they're actually pulling on the shared electrons a little bit harder than the other atom. So what ends up happening is they draw the electrons a little bit closer to themselves, which causes that end of the molecule to have a partial negative charge because electrons are negative. So if you're pulling them closer to yourself, you'll have a partial negative charge. And then the region, the atom that has the electrons further away from them, they're going to end up with a partial positive charge because their nucleus has a positive charge and the electrons are being pulled slightly further away from them. So this unequal sharing is indicated by a dipole. So you can draw a dipole. And it's this little arrow, and then there's like a little plus sign on the back end of it. And it's always pointing toward the more electronegative atom. You can also show the unequal sharing by writing that partial positive symbol and that partial negative symbol. So this is going to make a lot more sense when I go over a couple of examples. So we're going to start with sulfur and oxygen. So what ends up happening is if I look at sulfur's electronegativity on the electronegativity table, it's at a 2.5. And oxygen is at a 3.5. So the difference in electronegativity is going to be 1.0. And 1.0 is greater than 0.5. So this is going to form a polar covalent bond. All right. So oxygen is clearly more electronegative. So if there's a pair of electrons here, what that means is that the electrons aren't being shared equally between the two. No, in fact, what is happening is that the electrons are getting pulled slightly closer to oxygen. And because they're closer to oxygen, oxygen's going to end up with a partial negative charge because oxygen is pulling negatively charged particles closer to itself. And then sulfur is going to end up with that partial positive charge because the electrons have moved further away from it. So again, that partial negative, partial positive is a way to show that dipole or the two poles that you've created, right? So here's my partial negative pole and here's my partial positive pole. The other way that we're going to depict this is by drawing that dipole arrow. So you would always be pointing at the more electronegative atom, and that's oxygen. And then that little plus end ends up on sulfur. And again, that tells us that that sulfur end is going to have that partial positive charge, and that oxygen end is going to have that partial negative charge. All right, so let's try it again with another example. So we've got fluorine and chlorine. Fluorine, if I look at the table, has an electronegativity of 4.0. Chlorine is at 3.0. So their difference, it's carbon, sorry. Carbon is 2.5. So fluorine and carbon. So I can see that the difference here is a 1.5 difference in electronegativity. Remember, that difference is greater than 0.5, so this is going to be a polar covalent bond. And if I'm thinking about drawing it with the arrow, I'd be pointing at my more it doesn't matter if the arrow is above or below the bond, so this time I'm going to draw it above. It's going to be pointing in the direction of fluorine. The little positive end will go toward carbon. Now remember, that means that those electrons, and you don't ever have to draw this part right now, we'll talk about drawing later. The fluorine, that means that the electrons are getting pulled closer to fluorine than they are toward carbon. And remember, those are negatively charged. So that means that this fluorine end of the bond is going to have that slight negative charge. Whereas the carbon side, because the electrons are getting pulled away from it, is going to end up with that slight partial positive charge. All right, one more time. We're going to do hydrogen and oxygen. Hydrogen has an electronegativity about 2.1 if I look at my table, and oxygen has an electronegativity of 3.5. Again, it's going to be up here, so we'll be using this chart a lot. So oxygen 3.5, hydrogen's at 2.1. I come back down here and I take a look, and I can see that the difference in electronegativity is a 1.4. You don't have to do negative numbers. You just use whatever's highest and subtract whatever number's lowest. So the difference in electronegativity is 1.4. Their difference in electronegativity, again, is greater than 0.5. So again, this is going to be a polar covalent bond. And if I were going to show this using my dipole, again, I would be pointing at the more electronegative atom, which in this case is oxygen. So oxygen is sharing the electrons unequally by pulling them closer to itself. That means that those shared electrons are further away from hydrogen, so I put that little plus N close to hydrogen. That also tells me that this end of the bond is going to end up with that partial positive charge, not a whole positive, just a partial positive, because it still has the electrons. The electrons are just further away from hydrogen. And those electrons are closer to the oxygen, so that gives oxygen that partial negative charge. So again, these are polar covalent bonds. They're still covalent bonds. It's still a nonmetal to a nonmetal. But in this case, their difference in electronegativities are higher than 0.5, so it does affect how the electrons are shared between the two. The last type of bonds I'm going to go over quickly in this set of notes. We don't go into very much detail about them, but I just wanted to bring it up. These are metallic bonds. And so when metals are bonded to other metals, if you have elemental metal like all gold, or if you have alloy metal, essentially what's happening is that they all have low electronegativities. So their valence electrons are not tightly bound to the nucleus. And so what ends up happening is that they lose those electrons pretty easily. And the electrons form what is sometimes referred to as a sea of electrons. So the electrons sort of move freely about the space, and so you get, again, this sort of like sea of electrons when your metals lose those electrons because they have the low electronegativity. But because the sea of electrons has this negatively charged space that has now been created, the metals are now attracted to it, so they sort of stick to that sea of electrons, and that's how your metallic bonds end up forming. So again, It's the force of attraction between the free-floating valence electrons, that sea of electrons that forms when the metals release their electrons, again, because of that low electronegativity. And then we have these positively charged metal ions that are now attracted to that sea of electrons, and that's sort of what holds them together. So again, we don't go into a ton of detail about metallic bonds. We'll go into a lot more practice with covalent bonds and ionic bonds moving forward in class.